Hello, carrying on with the Oxford PAT from 2019, we're up to question 13. So they're asking us to sketch the graphs of y equals 1 plus x to the n for integer values of n from 0 to 3, each on a separate set of axes. Which point or points are common to all of the graphs? Right, so I'll just do small sketches so I can get them all on side by side here. So that's the 4 set of axes. So we've got, first of all, y is equal to 1 plus x to the power of 0. So that's just going to be a horizontal line going through 1. Then we've got 1 plus x to the power of 1. So that's just 1 plus x. So that's going to be a straight line going through minus 1 and 1 on there. Then we've got y equals 1 plus x all squared. So shifting it, again, we're just shifting everything across to the left by 1. So that's that one. And then we're going to have the same shift to the left again for our cubic going through minus 1. Oh, they're going through 1. So everything, the common point, yeah, we've only got one common point at 0, 1. 0, 1 is our common point. So that was a fairly straightforward set of 4 marks. Describe 2 of the further features common to the graphs for integer n greater than 1. Right. Well, I suppose in that case we could say, well, they're all going to now go through this point at minus 1, 0. So they all go through minus 1, 0. What else could we say about it? We could say that the gradient is greater than 0. Do you want to go gradient greater than 0 for x is greater than minus 1? Could say that. I mean, you've got to say something about the gradient is all I'm thinking here. We could say the gradient is going to be equal to 0. X is equal to minus 1. We could have that. I don't know, I'm not really sure. I suppose these are common features. They're not particularly exciting common features, but y is going to be greater than 0 for x is greater than minus 1. I don't know. I mean, they're all going to have those features about them. None of them are that exciting, but anyway, that will do. I don't know what else to say about that last part. I mean, they're certainly common features, so that should be enough to get marks. Right, so we've got now radioactive sample with 2 isotopes A and B. A decays to B with a half-life of T1/2. B is stable. The number of atoms of A left after time T is given by that. Derive an expression. Oh, right, okay, we've got to derive the decay constant. Right, that's pretty straightforward. So we're saying then in that case that NA over N, well, A0 is going to be equal to half when is equal to e to the minus lambda T1/2. So we just have to rearrange all of this to make, what are we trying to get? We're trying to get lambda as the subject. So we're going to have the e to the lambda T1/2 is equal to 2. So lambda is going to be equal to log 2 divided by T half-life. So that was fine. Initially, the number of B atoms is NB, okay, or NB0. Let N be a T be the time-dependent number of B atoms in the sample. Write down an expression for NB of T. Okay, right, so the NB is going to be equal to, well, our initial number, because we've got a fixed amount of stuff here. So it's going to be, we can add on everything that we had for A, all the original A stuff. So NA0, and then take off what's left, which is NA. So this is what we need in all of this. So that is going to be what we got. So we can replace what NA is by this because they're the same thing. So that's NB0 plus NA0, 1 minus e to the minus lambda t. Is there anything else? So they want it in terms of lambda, NB0, NA0, and T. Yeah, which is all we've got in there, so that's fine. We don't have to do any more arranging with that. But yeah, it's just because the total amount of stuff must be the same all in all. So yeah, if we've got the original, I suppose another way of writing this equation, just in case you're wondering where it's come from, is saying, well, the initial amount of stuff which we've got, which is the total amount of B plus the total amount of A, is going to be whatever amount of B plus whatever amount of A we've got some other time. This must always add up because we're not losing any of our sample here. It's either A or it's B. It's not going off anywhere else, and that's just rearranged into this equation here. So that's fine. At the start, there are X times as many A atoms in the sample as there are B atoms. How long does it take for this ratio to reverse? Right, let's scroll down a little bit, give a little bit of space. So we're starting with, what did it say there? X times as many A as there. So NaO is going to be X times NbO. That's what we started with. And we need to get to X lots of Na equals Nb. That's what we're after. So that is, what have we got on all of these? So we need on this that X, so Na is, well, it was, I don't need to scroll up, it's NaO e to the minus lambda t. So that is our X times Na. And that needs to be equal to Nb, which we've just written out, NbO plus NaO 1 minus e to the minus lambda t. Excellent. And we've got this relationship here between NaO and NbO. So we can put those in. So we're going to get, let's replace all these, well, there's these two NaOs there. So that'd be X squared NbO e to the minus lambda t is equal to NbO plus X NbO 1 minus e to the minus lambda t. So we can cancel all these NbOs, get rid of that, get rid of that, get rid of that, so there's a 1. So what have we got left with on all of this? We've now got that well, let's make that, I'm going to have to write this out again, I've crossed that out, but I now can't see what I'm doing. So we've got X squared e to the minus lambda t, 1 plus X minus X e to the minus lambda t. Scroll down a little bit more. So let's factorize these e to the lambda t's somewhere. So we're going to have X squared plus X e to the minus lambda t is 1 plus X. E to the minus lambda t is therefore going to be equal to, but we can get rid of these x's. We can remove an x on one side. Oh, so that's just going to cancel on both sides, isn't it? Yeah, because we've got x plus 1 divided by, I've got too many x's going on here, over x plus 1. So yeah, so those, no, I've got the right amount there, so they're going to cancel. So we've got e to lambda t is equal to x. That's good. So x is t is going to be log x divided by lambda. Is that what I wanted? So yeah, how long does it take for things to reverse? Yeah, okay, that was quite fiddly. That was quite an involved question, but yeah, conceptually okay, but it was quite fiddly. Oh my word, this looks like something else. An air cell refractometer. So what does this thing do then? So we've got this beam of light coming in from the entrance window. So they're going in normal, so it doesn't refract there. It's then going to hit this glass, which is going to refract it towards the normal, then the air away from the normal, then the glass towards the normal, and then the liquid is going to come back out parallel again. Okay, so we're going to end up having a beam coming out somewhere at the bottom. So as we change this angle, then we're going to get a different exit point for the beam on the way out. And then that presumably is going to tell us something about the refractive index of the liquid. Right, so what's it saying here? We got this beam of light comes in the entrance window, normal incidence, yeah. See it coming out the bottom, the outer box, yeah, it's just describing everything that's in the picture. It's not saying anything. So the angle can be precisely adjusted and measured. On the diagram provided on the next page, draw the refracted path of the beam through the air cell. So the refractive index of the glass is more than the liquid is more than air. Right. Oh, well, no, drawn that super big. So yeah, if you're in the same medium, it's going to end up being parallel. So we want to have a vertically down line when we go out the bottom. The glass ones are going to be parallel to each other. So glass is more than the liquid, so it goes towards the normal. The air is, not only is it less than the glass, but it's less than the liquid. So it needs to be going to the right as a vertical line looks. So it needs to not be just going straight down. So yeah, we can't have some weedy little refraction where it's just moving away from the normal, but it's still to the left of the one in the liquid. It has to be to the right. The path has to be to the right of what we saw in the liquid, because air has got a lower refractive index, so it must be further away from the normal. Then when we get into the glass again, it's going to have to be parallel to the original glass line that I drew. So these two lines have got to be parallel to each other, and then when you hit the bottom, it needs to be coming out straight down so that it's parallel to the initial beam. Right, so yeah, that's not too bad to draw. Describe qualitatively what you will observe at the exit window as you increase theta I from 0. Hence, explain how this instrument could be used to determine the refractive index of the liquid. Right, let's go to the smaller picture. Right, so if it was 0, then you've just got the block there and it's going to go straight through. So as we then tilt it off to the side, the spot is going to move, isn't it? Our exit point is going to move. So because it's going to be coming down, doing that, then that, then that. So that's going to keep on moving in some fashion until eventually it's gonna, yeah, so right, okay, which direction is it going to move in though? Because we're turning it that way, it's going to be moving, the exit beam's going to be moving off to the right, isn't it? I believe would be the case. So if we come down there, then it's moving further. Yeah, this is the thing that's changing it, isn't it? Eventually we're going to hit a critical angle on this. So the bigger, yeah, if we've got all of these, right, let's mark on, actually I'm going to go back to this one here. So we've got this angle here, theta 2, and then we could say we've got another angle here, theta 3. Then when we get back to here, that's going to be theta 2 again. So that's our theta 3 there. See, it's a bit sketchy drawing it all on here. And then we're going straight down where that angle is going to be theta I. Do they call it I or 1? I. Okay. So theta I. So what we're saying here so if theta I goes up, then theta 2 will go up until theta 3 is until is the critical angle. Yeah, this is where we're going to get our total internal reflection. Until, so theta 3 equals 90 degrees, i.e. total internal reflection. So that's what we're going to have on this. So what we need on this is to say the beam, the exit beam, will move until we get to total internal reflection at the glass air boundary. and then it will disappear. Then we won't see it anymore. So we need to mention that as well. So then light disappears. And they wanted us to work out, I believe it was, what was it, a relationship between NL and theta I. Right, so at that point then, so we've got the NL sine theta I, so this is Snell's law on the way in, is going to be equal to NG sine of, what do I call it, theta 2. And then when the light disappears, then we're going to have that NG sine theta 2. So where are we? Yeah, so this is NG sine theta 2 will be equal to NA at total internal reflection. So that will be when, yes, so that, yeah, this is exactly what we want. So that means that sine theta I is going to be equal to NA over NL. And that's what we're then measuring. Right, so yeah, you keep measuring it, keep increasing the angle until it disappears, and then it's giving you that ratio. And that fits because the refractive index of the liquid is more than the refractive index of air, so that's going to keep this below 1, which is exactly what we want. Right, so that's good. Suggest with reasons a way to modify the apparatus or its use to improve the measurement. Right, so the thing we're measuring is theta I. So to improve that, so we want that to be as big as possible. So we want to increase theta I to excuse me, to reduce the percentage error on measurement. Percentage error on measurement. So if we want to increase that, then that means, therefore, we want to, what do we want to do? We want to get a higher NA then. We want to make this bigger. So therefore, we want to increase NA, therefore replace air with something which has got a higher refractive index. So maybe with gas of higher refractive index. So it's, I mean, it still has to be less than the refractive index of glass, but that, yeah, that was quite a nice question actually. It was, yeah, a lot to deal with, especially having something new. This seems to be the thing that they like on these more recent PAT papers, that they give you things that are completely new and see if you can figure them out as you go along. A bit like it looks like this one's going to be. So energy levels of the electron in a hydrogen atom are characterized by a quantum number n, which is that. Oh, it's this Rydberg or Rydberg constant again. This came up a couple of PATs ago. State a formula that relates the wavelength of light to Hc and E, which is the energy of a photon. Oh, right, okay, yeah. So we've got the, well, E is Hc over lambda, because that's E equals Hf. And we want to make the wavelength the subject, I suppose, so Hc over E. That's good. Let P and Q be the quantum numbers for the upper and lower energy levels of an electron transition in hydrogen. Find a formula that relates the wavelength of light emitted in such transitions to P and Q. To P and Q. Oh, right. Transitions, right, so relate the formula, right, to P and Q. Right, so that's what we want to get. We want to get lambda as a function of P and Q, is what they're saying. Okay, we don't have a lot of space for doing all of this. Maybe I'll scroll up. There, we've got space at the top. So we're gonna, well, our energy release is going to be, so P is the higher, so we're going from P to Q. So we need to do the Q one first, which is going to be the, oh, it's, well, if we're subtracting them, oh, and they're negative, so okay, yeah, so it's going to be the EP minus EQ is what we're doing here. So it's the energy difference between these. We're moving to something which is more negative. So this will give us a positive number when we subtract the more negative thing from the less negative thing. So we're doing EP. Let's actually put that in. EP minus EQ, which is then going to be HCR over Q squared, because that will become the positive one, minus HCR over P squared. So that is HCR. What am I doing? Oh, we need to work out. I don't even know what I'm trying to work out now. I've lost where I am. Oh, we want to work out the wavelength of this. Right, so we've got HCR. So HC is lambda E. Oh yeah, this is what we're doing. Yeah. So HC divided by all of this is what we're trying to do. Right, yeah. So busy talking about P's and Q's, I forgot where I am. But let's work out this thing first. So we've got HCR P squared minus Q squared over P squared Q squared. And we need to now put it into here and say that lambda is HC divided by this. So the HC's are going to cancel. We're going to get an R on the bottom. So that means that our lambda is going to be this thing in the bracket upside down with an R on the bottom. P squared Q squared over R P squared minus Q squared. Right. So yeah, that was just working out this and sticking it into, oh, not that one, into that one. Excellent. Right, for each of the three hydrogen emission line sets shown in the table below, identify the quantum number of its lower energy level Q. Okay, so let's write down this thing again then. So we had lambda was equal to P squared Q squared over, what was it? R P squared minus Q squared. R P squared minus Q squared. Each set, so column, okay, right, so we've got three sets, A, B, and C, of 5 emission lines. Yeah, these 5. That's the same lower energy level. They've all got the same Q. The first column shows the quantum number of the upper level. No, it doesn't, does it? First column shows the quantum number of the upper energy level Q relative to the lower level. That'd be, they mean P, I think. Right, you can assume that P is less than 6. Well, isn't it going to be easier just to plug things in then, since we've got so few numbers, and we can just look at the first row? So yeah, let's do that. So if P was 5 and say Q was 4, so we're looking at P is Q plus 1 is what I'm doing here. So if P is 5, Q must be 4. So if we put these in, we're going to get the, oh, they're giving us R there. So what have we got? We got P squared times Q squared. So that is 25 times 16 over 25, so 9R. 25 times 16 is going to be 400. So 400 over 9R. Just stick that into the calculator and see if it comes up with any of these numbers. And yeah, it does. It's come out of this one. Right, so that's going to be B then. So what do we want? We want to relate, assume that. First column shows that, yeah. Identify the quantum number of its lower energy level Q. Right, so for B, we've got Q equals 4. Then what if we change these again then? So we could have P equals 4, Q equals 3, which means we're going to have 16 times 9, 144 over 16 minus 9 is 7R. So just change that around. I've still got it sitting in the calculator. No, it doesn't look like either of those numbers. So P equals 3, Q equals 2 will be, what's that going to be? 36 over 5R. Change that. No, that's not come out. Right, this is now causing a problem because well, this must be 1, you'd have thought. P is 2 and Q is 1. Yeah, that's just going to be 4 over 3R, which, yes, has come out at A. So that's given us that one, which has got Q is equal to 1, but we got nowhere else to go with Q. Can't go down to Q is 0. So what do we do with this? Maybe they've done another typo. Can we go up to P is equal to 6? I mean, they've said P is not. Well, I don't really. Well, I'll try that. If not, I don't know where to go now. So P is 6, Q is 5. Let's try that then. So that'll be, we got all of this. We've got now 36 times 25 over 11R. Is that going to come out of the 7460? Yeah, it does. Right, okay, so that's not true actually. So that should be less than or equal to 6. So we got Q is 5 for that one. Well, that was a bit of a lame question. That was just plugging in numbers, trial and error. Maybe there's a different way of figuring that bit out at the end, but for 4 marks, that seems like a reasonable amount of work to do for 4 marks. I don't know, not a particularly satisfactory question all in all. Am I going to stop here or maybe do one more? Oh, it's the geometry one, so these are normally fairly quick. Yeah, okay, I'll do it. I'll put it in. Might be quite a long video. Find an expression for the angle theta for which the grey area is f times the area of the outer square. Okay, right, so let's get a bit of an equation then on this. And so grey area, how are we going to do that? That is going to be the area of the square minus the area of the big circle plus the area of the little circle, but then we've got the issue of this chunk, so that's going to be add on a big sector, but then we would have double counted this little bit, so take off a little sector. Right, that's quite a lot of things to work out on all of that. They've given us and what is that equal to? F times the area of the outer square, so that is F times, well, the area of the outer square. Oh, they've given us the diameter of the square, haven't they? Because it's, yeah, the radius of the circle is half the diameter. So we've got XR. So we're gonna we'd have to multiply that by, well, it'd be 4 times, because if you do XR squared, you're going to get a quarter of the square. So 4x squared R squared. That's our area of the, well, actually, that's just going to cancel on both sides anyway, isn't it? So it doesn't really matter about that. We can just get rid of it. Oh no, it's not going to cancel because you've got a factor of f. Right, so this is going to be 4x squared R squared. The big circle is then pi x squared R squared. Then we've got, oh, we're taking that off, not adding it on. Then we're adding on the little one, which is pi R squared. Then we got to add on the big wedge. So the big wedge is equal to, well, it's going to be theta over 2 pi times the area of the big circle. So pi x squared R squared. Then we got to take off the little wedge, which is going to be theta over 2 pi R squared. Right, that's a right mess, that, isn't it? Well, we can get rid of R squareds everywhere, and at least I can get a bit more space to try and figure all this out. So we got 4fx squared, that's our bit up here, and that is going to be equal to 4x squared, just get rid of all the R squareds, pi x squared plus pi, plus those pi's are going to cancel there. So theta over 2x squared minus theta over 2r squared. So I could really do with getting rid of these over 2's, I think. A 2 there, a 2 there, an 8 there, and an 8 there. Okay, so we're now going to want to, what am I even trying to do here? I just want to get theta as the subject on all of this. Oh, I got rid of that r squared. Yeah, don't need that. So yeah, make theta the subject on all of this. So we've got on all of it, yeah, we've got these various, I've got so many x squareds kicking around here. Seems to be loads of them. Do I want to factorize the pi's or all of the x squareds? Let's go with what have we got in this answer here? Yeah, we've just got, I don't know, I'm going to go with the pi's. So we've got because I want to get these x squareds, we've got an x squared minus 1 there, which I think is going to be nice on all of these things, because this is what's leading me to this factorizing the pi's there, because that's going to be a 2 pi x squared minus 1 on the other side, which kind of fits with the format of the question. And then we've got an 8 x squared f minus 1 plus that. Right, is this looking anything like, because then I can divide through by the x squared minus 1. So we've got that theta is going to be equal to 2 pi plus 8 f minus 1 x squared over x squared minus 1. So how does that look like what we had up here? So we want b, right, let's just move this down because I can't see what I'm trying to do. So this is the format that they want. C of f x squared over x squared minus 1. That certainly has similarities to, right, so we've certainly got the b, we've got some function of f, we've got the x squared, we've got an x squared minus 1. Oh, they've weirdly put a minus sign in there, but yeah, we've got, so that's fine, because it means that b is going to be equal to 2 pi, and it means that we've got c is equal to 1 minus f. So, although, yeah, I suppose that does make a bit of sense, because f is going to be less than 1, isn't it? So, yeah, it makes sense to write it that way round. But yeah, it's fitted into that format, which is exactly what we wanted. So that was quite a nice question to piece together. And oh, there's still more of it. So yeah, we've done all of that. Find the numerical value of theta to 5 significant figures when x is 3 and f is a half. So x is 3, f is a half. So that means that theta is equal to 2 pi plus, well, we got 8 times a half, so 4 times 9 over 9 minus 1. Right, so that is 2 pi plus 9 over 2. And I wanted this to, I mean minus, because I've just changed this around, haven't I? Is that right? Oh no, where was I on this? 8, which one have I put in? Yeah, I've done, yeah, it will be a minus, so I've still been working off of this, but I have done 1 minus f. Right, let's write this out again to make sure I'm getting this right. So, yeah, because we've got 1 minus f. Yeah, let's rewrite this to get it in the proper, yeah, that 1 minus f x squared over x squared minus 1. So, yeah, we've got a minus here, not a plus. Minus there, not a plus. So, 2 pi minus 9 over 2. And we wanted that to, how many? 5 significant figures. Right, okay, let's just tap it in the calculator then. So we got 1.7832. So 5 significant figures. Right, there we go. So yeah, that last part nearly tripped me up by losing that minus sign. That was the thing, when they rearranged this, yeah, make sure that you don't fall into the same trap I did on that one. Or nearly did. At least I managed to reverse it at the last moment. Right, I'll leave this one here because we've gone through quite a lot of this. This is a really long video now, I think, and come back in the next one for the remainder of the paper.